welcome to Science. Today we are talking about octonions, 8-dimensional numbers with unusual properties like non-commutativity and non-associativity. This episode will be a lot to take in, but stick with it. Even if you need to rewind a few times to grasp these complex theories, we promise they will help your imagination explore. While octonions have long been considered by mathematicians, physicists are now investigating their potential applications in describing the fundamental particles and forces of the universe. Octonions could provide a framework for unifying the fundamental forces of nature and shed light on the mysteries of particle physics, string theory, and quantum gravity. Despite their potential, octonions remain a highly speculative area of research, and their application to physics is still largely theoretical.
All right, buckle up, everybody, because today we're going deep into octonions.
Yes.
You guys sent in a ton of stuff.
Yeah.
A whole bunch of articles and research on this 8-dimensional number system. And I got to tell you, some of the stuff that's in here, it's really...
it's pretty wild.
Yeah, string theory and quantum mechanics and even...
A theory of everything.
A theory of everything.
Yeah.
I'm super curious about all this.
Yeah. Well, it's not surprising you're finding it intriguing.
Yeah.
Octonions tend to do that. They're a bit of a hidden gem in mathematics.
Yeah.
But the history is surprisingly rich. and their potential connections to like the fabric of reality, I mean, they're definitely worth exploring.
Okay, so before we get too far into the weeds here,
Yeah.
can we even try to explain what octonions are in a way that won't like totally break our brains? Mm-hmm. I keep picturing like a souped up hypercube or something, but I have a feeling that's not quite right.
Yeah, I mean, the hypercube is good if you're thinking about higher dimensions, but octonions are a little trickier.
Okay.
The best way to think about it is to think about how they sort of build on number systems we're already familiar with.
Okay.
So start with real numbers.
Yeah, the ones we use every day.
The ones we use every day.
Yeah.
And then add in the imaginary unit.
Okay.
So the square root of -1, and boom, you've got complex numbers, which are essential for quantum mechanics.
Right. Those are old friends by now.
Yeah.
So is it kind of like building a number tower?
Yeah.
Like each level gets...
That's a great way to think about it.
More dimensions, more complexity?
Yeah, absolutely.
Okay.
So next up is quaternions.
Okay.
Those are 4-dimensional, and they have 3 imaginary units, I, J, and K.
Okay.
And those are great for rotations in 3D space, like computer graphics, special relativity.
So octonions are like the penthouse suite of this number tower.
Exactly. So we take those quaternions and we add 4 more imaginary units. We end up with octonions, our 8-dimensional system.
All right.
But here's where things get really interesting. This added complexity comes with some, shall we say, quirky behaviors. So in the sources you sent, they talk about how they're non-commutative and non-associative.
Yeah, those are the terms that really stood out to me.
Right.
I think I get non-commutative.
Yeah.
That the order you multiply in matters.
Yeah. A times B doesn't equal B times A.
Okay.
But non-associative.
Yeah, that one's really weird.
Yeah, that one's really weird.
It feels like it breaks all the rules.
It seems that way.
Yeah.
And it's one of the reasons why octonions haven't always been taken seriously.
Okay.
But think of it this way. Putting on your socks and then your shoes is a totally different experience than trying to put on your shoes and then your socks.
Right. Yeah, that makes sense.
It's kind of like non-associativity. The order you do things, or in this case, multiply numbers, makes a real difference.
Okay, I like that analogy a lot.
Oh, good.
So we've got these weird 8-dimensional numbers that seem to break all the rules of math as we know it.
Yeah.
But one of the things that really blew my mind was this idea that the real numbers, complex numbers, quaternions and octonions, are the only 4 normed division algebras.
It's amazing.
It's like nature decided to stop there.
Yeah.
Like, why?
It's a question that's puzzled mathematicians for ages.
Yeah.
The fact that there's only 4 and they each build on the last one.
Yeah.
It feels almost intentional.
Like there's some deeper structure or something.
Yeah, like there's some deeper structure dictating how numbers and maybe even reality itself are organized.
Like there's a secret code in there.
Exactly.
Okay.
And speaking of codes, let's talk about the history.
Yeah, where did these mysterious octonions come from?
So back in 1843, a mathematician named John T. Graves, he discovered them right after his friend William Rowan Hamilton discovered quaternions. And then Arthur Cayley stumbled upon them independently.
Wow. So they've been around for over 150 years. Just kind of waiting for us to figure out what they're for.
In a way, yes. But it's only recently that like physicists have started considering how they connect to the bigger picture.
Okay, so we've got complex numbers that revolutionized quantum mechanics, quaternions, that help us understand space-time.
Right.
Would octonions be the next big thing?
Yeah, that's the question. Could they be the key to unlocking even deeper secrets?
So tell me what the sources say about their potential role in physics. What kind of whispers are we hearing about their connection to string theory and all this other stuff?
Well, so remember how we talked about octonions being 8-dimensional?
8-dimensional,
So one of the most promising areas is string theory, which suggests our universe might have more than just the 4 dimensions of space and time.
Right. More dimensions than we can perceive.
Yeah, the ones we perceive. So octonions could be the mathematical key to understanding the geometry of those hidden dimensions.
Whoa, okay, so they could help us map out these invisible dimensions.
Yeah, it's pretty wild.
What else?
They also pop up in grand unified theories. Or GUTs.
GUTs,
which try to unify the fundamental forces of nature, the strong, weak, and electromagnetic force, into one elegant framework. And octonions are linked to these things called exceptional Lie groups.
Now symmetry groups, those are basically just...
They're mathematical ways.
Mathematical ways of describing.
Yeah, of describing how things stay the same. Even when they're transformed, like a snowflake. You can rotate it 60 degrees and it still looks the same. That's a type of symmetry. So in particle physics, these symmetry groups describe how particles behave under different transformations. And octonions might be connected to the underlying symmetry of the universe itself.
So not only could they help us understand the hidden dimensions of the universe,
potentially,
but also the fundamental symmetry that holds it all together.
It's pretty amazing.
This is incredible. Are there any other areas where they kind of make a cameo appearance?
Absolutely. There's also quantum gravity, which basically seeks to reconcile quantum mechanics with general relativity. So, you know, merging the physics of the very small with the physics of the very large. And some theoretical frameworks for quantum gravity are using octonions to describe the very fabric of space-time at the tiniest imaginable scales.
So octonions could help us understand
potentially
what happens where quantum mechanics and gravity meet.
Where
the rules of reality, as we know them, break down.
That's right.
This is wild. It's like we've stumbled onto a secret code that might unlock some of the biggest mysteries in the universe.
It's possible.
But the sources also hint that there's still a lot of work to be done.
There are definitely challenges.
It's not all sunshine and roses.
It's not all sunshine and roses.
In Octonian land.
No, it's not.
Right.
It's one thing to find all these like intriguing connections, but it's another thing to actually build like a complete theory. You know, a self-consistent theory based on octonions. That makes testable predictions. It's like having all the pieces of a puzzle, but not knowing how they fit together.
So it's like we have this toolbox full of shiny new octonial wrenches and screwdrivers.
Exactly.
But we don't know what we're building yet.
We don't know what we're building. And remember that non-associativity we talked about that makes working with these things really tricky. It's a mathematical beast that we're still trying to tame.
But even with those challenges, it sounds like some researchers are starting to make some real progress.
There are.
The sources mention this Ko-Fury.
Yes, Ko-Fury
was doing some groundbreaking work connecting octonions to the standard model.
Right.
Which she discovered that has everyone so excited.
Well, what's really fascinating is that she's using this combination of all 4 division algebras, the real numbers, the complex numbers, quaternions and octonions.
So she's not just focusing on octonions in isolation, but seeing how they fit into this larger mathematical ecosystem.
She calls this the Dixon algebra.
Dixon algebra.
And within that, she's found some remarkable echoes of the standard model.
Like what?
So, for example, it seems like the Dixon algebra just naturally produces the symmetries associated with both space-time and the standard model forces.
Wait, so the same mathematical structure that might describe the fabric of the universe also seems to describe
potentially
the fundamental forces.
It's pretty mind-blowing.
That's a huge connection.
It is, and it gets even more interesting.
Okay.
So she's also found these hints of a 10-dimensional space-time structure.
10 dimensions.
Yeah.
Embedded within the Dixon algebra.
Right.
Oh, so hold on. Now, didn't you say that string theory predicts 10 dimensions?
Yeah.
Is that a coincidence or?
No, that's the million-dollar question.
Or are we seeing like a deeper connection here?
Yeah. That's what makes her work so compelling.
Yeah.
Because it's like these different areas of physics are starting to converge.
Okay.
And it's as if the Octonions are providing a bridge between string theory and the standard model.
That's really interesting.
Yeah.
Okay. There was also something in here about Furey's research potentially explaining the quantization of electric charge.
Yes.
So can you unpack that a little bit?
Basically, electric charge always comes in these discrete units.
Okay.
Like the charge of an electron or a proton.
Right.
We've known that for like over a century, but we've never really understood why charge is quantized.
Oh, okay.
And Furey's models suggest that this quantization might just emerge naturally from the properties of like whole numbers within the Octonions.
So the very nature of these 8-dimensional numbers might explain one of the most fundamental properties of the universe.
It's possible.
The fact that electric charge comes in these neat little packages.
Yeah.
It's like those old video games.
Yeah.
Where you can only move in like blocky increments.
Right.
It's like the universe itself is pixelated.
I love that analogy.
Okay.
So while Furey's work is really pushing the boundaries here, she's not the only one exploring the potential of Octonions. So you sent some sources that also mention the exceptional Jordan algebra and this two-sheeted universe.
Okay, what in the world is the exceptional Jordan algebra?
So the exceptional Jordan algebra, or EJA, is this 27-dimensional mathematical structure discovered by Pascual Jordan back in the 1930s.
All right.
And it turns out this algebra is closely related to Octonions.
Okay. How so?
You can think of it as like a way of organizing 3x3 matrices of Octonions.
Matrices of Octonions. We're really going down the rabbit hole here.
Yeah, right.
Okay, so how does this connect to the idea of a two-sheeted universe?
There are these two physicists, Latham Boyle and Neil Turok.
Okay.
And they're using the EJA to explore this idea.
Okay.
So imagine our universe as like a sheet.
Okay, a sheet.
A membrane. Floating in some higher dimensional space.
Okay.
And then picture another sheet, like a mirror image of our universe floating nearby.
Okay.
And that's the basic idea behind this two-sheeted universe model.
Okay.
So according to Boyle and Turok, these two sheets kind of interact through a mirror reflection.
So it's like our universe has a twin.
Yeah.
And they're communicating.
Yeah.
Through some kind of cosmic mirror.
That's a fun way to visualize it.
Okay.
And the really wild part is that they believe that the EJA, with its connections to Octonions, might be the right mathematical framework.
To describe this two-sheeted universe.
Yeah, to describe this two-sheeted universe.
It's blowing my mind.
I know, it's pretty wild.
It's like all these threads are weaving together. Octonions and the standard model and string theory and multidimensional universes. And now this exceptional Jordan algebra.
I know, it's a lot.
It's like we're on the verge of uncovering like a grand unified theory of everything.
Maybe.
But the sources also mention some potential roadblocks.
Yeah, there are.
Like these things called zero divisors.
Right.
What are those and why are they a problem?
Okay, so zero divisors. They're kind of a quirk. That pops up when you start dealing with algebras that go beyond the familiar ones, like real numbers and complex numbers. They're basically non-zero numbers. That when you multiply them together, they give you zero.
That seems counterintuitive.
It does. It seems counterintuitive, but it's a consequence of these strange rules that govern these higher dimensional algebras.
Okay, so how do they mess things up?
Right. So,
and we're trying to use octonions to describe the universe.
One of the things that makes normed division algebras so special is that they don't have zero divisors.
Okay.
So that means that division is always well-defined, just like with regular numbers.
Okay.
But as soon as you go beyond octonions to like even higher dimensional algebras, like the 16-dimensional Octonions,
okay.
you start running into these zero divisors.
So octonions are like the edge of a cliff.
Yeah.
The last stop before we plunge into the abyss thanks of zero divisors.
That's a great way to put it.
Okay.
And that's one of the reasons octonions are considered so unique.
Okay.
They're like the largest possible normed division algebra.
Okay.
The most complex system we can use and still like hold on to these familiar rules of arithmetic.
So they strike this delicate balance between order and chaos.
Yeah, exactly. And that balance might be what makes them so relevant to understanding the universe, which itself seems to exhibit both order and chaos.
Okay, so octonions are the edge of the cliff.
Yeah.
The last bastion of well-behaved math.
Right.
Before we fall into the zero divisor abyss.
The zero divisor abyss.
But are the systems beyond octonions,
right,
the ones with zero divisors, completely useless?
So
could they have any relevance to physics?
That's a good question.
Or are they just mathematical oddities?
That's a question that's still up for debate. Some researchers think that even algebras with zero divisors might have some role to play in physics.
Okay.
You know, maybe in describing phenomena that are even more exotic than anything we've encountered so far.
Give me some examples.
Well, so some physicists have speculated that they might be connected to the mysteries of dark matter and dark energy.
Whoa, okay, so we're really going off the deep end now. Dark matter and dark energy are already huge puzzles.
Big puzzles.
Could zero divisors actually help us solve them?
It's certainly a possibility.
Right.
I mean, because we know so little about dark matter and dark energy.
Yeah.
It's conceivable that we need to expand our mathematical toolkit.
Okay.
You know, beyond the familiar territory of these normed division algebras to really understand them.
So zero divisors might be part of that expanded toolkit.
They might be part of that expanded toolkit.
That's really interesting.
Yeah.
Okay. Speaking of unexplored mathematical territory.
Yeah.
The sources you send also mention something called Mofang loops.
Mofang loops.
How do those tie into octonions?
So Mofang loops, they're this fascinating concept in abstract algebra.
Okay.
They're a generalization of groups, which are mathematical structures that describe symmetries and transformations. And the key difference is that groups require associativity, but loops don't.
So Mofang loops are like groups that have been set free from the constraints of associativity.
Yeah, exactly.
Okay.
And because octonions are non-associative, their non-zero elements don't form a group, but they do form a Mofang loop. So this means that they still have a kind of structure and symmetry, but it's a different flavor of symmetry than what we see with groups.
Okay, so how does this connect to the real world?
That's a great question.
What's the physical significance?
And to be honest, we don't have a definitive answer yet.
Okay.
Some researchers think that Mofang loops might be related to the fundamental symmetries of particle physics or even to the structure of space-time itself.
So they're like these.
Yeah, it's still an active area of research.
But patterns within the octonions?
Yeah.
That might point to some deeper
exactly.
organizing principle of the universe.
That's a beautiful way to put it.
It's like a secret message.
Yeah.
Encoded in the fabric of reality.
They're like whispers, hints of a deeper order that we're still trying to decipher.
This is amazing.
It is.
It's amazing to think that these really abstract mathematical concepts could hold the key to understanding the universe.
Absolutely.
But let's bring it back down to Earth for a second.
Okay.
You mentioned earlier that one of the biggest challenges is that no one's really been able to come up with a theory that makes testable predictions.
Right. It's like
what kind of prediction?
What would it take?
Are we talking about here?
Yeah, to convince physicists that this is more than just a mathematical curiosity.
Yeah. What would it take?
So to gain widespread acceptance, any theory based on octonions would have to make predictions that go beyond what we can already explain with like the standard model or other existing theories.
Right.
And those predictions would need to be
specific, measurable, something that experimental physicists could actually go out and test.
So we need that aha moment.
We need that smoking gun.
That piece of evidence that just screams, Octonions.
Exactly.
It's the Octonions.
Imagine if an Octonionic theory predicted a new particle with, very specific properties.
Okay.
Its mass chart, its spin.
Right.
If experimentalists actually discovered a particle that matched those predictions, that would be a huge win.
That would be huge.
For Octonions.
Okay.
Another possibility would be if a theory predicted some kind of deviation, however small, from the predictions of the standard model in certain particle interactions.
Right.
And if experiments could detect that deviation, that would also provide really strong support.
So it's not just about finding new particles, but looking for cracks.
Looking for cracks in our current understanding.
Yeah, in our existing understanding of physics. Cracks that might be filled by the Octonions.
Yeah, it's almost like...
It's like we need to listen very carefully to the universe and see if we can hear these subtle Octonionic whispers.
I love that analogy.
Okay.
It's about finding those subtle hints that point towards, a more fundamental, a more elegant explanation of reality.
This brings us to another interesting concept mentioned in the sources. Integral Octonions.
Integral Octonions,
Talk about those.
So integral Octonions are like a subset of Octonions with special properties, much like how integers are a subset of real numbers. They're like the whole numbers of the Octonian world.
So just as integers are used for counting discrete objects, could integral Octonions be used to count or describe?
That's a great
something fundamental in the universe.
It's a fascinating question.
Okay.
And while we don't have a definite answer, some researchers believe that integral Octonions might be connected to discrete aspects of physics, like the quantization of energy or the structure of quantum states.
So they might help us understand the quantumness of the universe, the fact that energy comes in these discrete packets.
Exactly. They also have these intriguing connections to certain lattices and symmetry groups that pop up in physics.
Like what?
For instance, they're related to the E8 lattice, which is this highly symmetrical structure that has been linked to both string theory and grand unified theories.
So even within the realm of Octonions, there are these hidden gems, like integral Octonions and the E8 lattice. That might hold further clues.
Absolutely.
It's like peeling back the layers
of
an infinitely complex onion.
Yeah, and with each layer we find...
And with each layer, more beauty, more mystery.
More beauty, more mystery.
Exactly.
All right, well, I think it's time to wrap up our deep dive into the fascinating world of Octonions. But before we go, any final thoughts?
Well, I think what's really striking to me is that even though Octonions are this relatively niche area of mathematics, they touch upon some of the deepest questions in physics.
It's true.
I mean, we've talked about their potential links to string theory, grand unified theories, quantum gravity, even the structure of space-time itself. But perhaps most importantly, they hint at this profound connection between mathematics and physics, this idea that
the universe might be at its core. Mathematical structure.
It's like the universe is whispering to us in the language of mathematics.
Exactly.
And we're just starting to learn the alphabet.
And maybe
Octonions are one of the vowels.
Maybe they are.
Essential for forming the words and sentences of reality.
That's a beautiful analogy.
It makes me even more excited to see where this all leads.
Yeah, me too.
So to everyone listening out there, if this deep dive has sparked your curiosity, keep exploring.
Keep questioning.
Keep questioning and keep wondering. Because the pursuit of knowledge is one of the most rewarding adventures we can embark on.
It really is.
Until next time.
We hope you enjoyed this episode of Welcome to Science. Welcome To is dedicated to exploring new technology to create informative and entertaining media. If you would like to create a podcast like this, be sure to visit Google Notebook LM. If you enjoyed this episode, please be sure to like and subscribe for more. Leave a comment if you have an idea for an episode that we should start researching. Thank you for listening.